All right, let's dive right in. We're going to break down the system design of a service like Pastebin. But we're not just going to look at some boxes and arrows. No, we're going to rebuild this thing from the ground up, from first principles, so you can really get why it's designed the way it is.
So I want to start with a statement that, well, it's probably going to sound completely wrong at first. Here it is. Pastebin is not a text-sharing app. I know, that sounds crazy. But trust me, if you want to design this system correctly, you absolutely have to get this core identity right from the very start.
So if it's not a text-sharing app, what is it? It's a life-cycle-managed, write-once object store. Now that's the mental model you need. Because if you start thinking about it in those classic database terms, create, read, update, delete, or CRUD, you are setting yourself up for a world of pain. Those update and delete ideas are going to lead you right down a path of unnecessary complexity and, frankly, system failure.
Okay, so to build this thing right, we have to start with the core principles. Everything else we design is going to flow from these two fundamental ideas. If you get these, you unlock a design that's simple, super robust, and can scale like crazy.
The first principle, and honestly the most important one, is immutability. It's simple. Once a paste is created, its content is set in stone. It never, ever changes. If a user thinks they're editing a paste, what's really happening under the hood is that we're creating a brand new paste, a totally new object with a totally new ID. This isn't just some small detail. It's the very foundation of the whole system.
Now here's the magic. Just by making that one decision, making data immutable, look at what you get for free. You can just throw away complex locking mechanisms. You never have to worry about write conflicts. Retrying a failed write becomes totally safe and simple. And because the content never changes, it is perfectly cacheable. It is literally the cheapest correctness guarantee you can buy.
Okay, principle number 2 is all about drawing a really hard line in the sand between two concepts that people always confuse: TTL expiry and deletion. TTL, or time to live, is about one thing: correctness. When a paste's TTL is up, it becomes logically invalid. Poof, it's gone, as far as the user is concerned. Deletion, on the other hand, that's just about economics. That's the janitorial work of reclaiming the physical disk space. They are not the same thing, not even close.
And this is the key takeaway. Your system's responsibility for being correct ends the exact moment a paste TTL runs out. Everything that happens after that, the cleanup, the garbage collection, all of it is purely a cost optimization problem. You cannot let the economics of your storage mess with the logic of your system's correctness.
All right, so we've got our two principles: immutability and the strict separation of TTL from deletion. Now let's see how those ideas actually shape the architecture. We're going to design the two most important flows of data: the write path and the read path.
So the write path is a nice, clean 4-step dance. First, we generate a unique ID. Second, and this part's really important, we write the actual paste content, the blob, to a dedicated object store like S3. Third, we write the metadata for that blob, so the ID, a pointer to where the blob lives, and that all-important expiry time into a real database. And finally, we just hand the ID back to the user. See that separation? Content over here, metadata over there. Beautiful.
Now, the read path. This is where those principles just shine. A user requests a paste. First thing we do, we fetch its metadata from our database. Then, right away, comes the single most important step. We check the TTL. We look at the clock and ask, is the current time past the expiry time? If the answer is yes, we stop. We immediately return an error, and we never even look for the data. If it's still valid, only then do we go fetch the blob from object storage and send it to the user.
And this visualization just makes it crystal clear. That TTL check is the absolute gatekeeper for correctness. A valid paste gets the green light, we go and fetch the data. An expired paste, it hits a brick wall. We return a not found error right then and there, and we save ourselves a super expensive trip over to the object store.
And this leads us to a rule that you can never ever break. It's a core invariant of the entire system. The read path must never wait for a deletion to complete. The whole process of cleaning up old data has to be completely separate, totally asynchronous from the user who's just trying to read a paste.
Okay, so the theory sounds pretty solid, right? It's clean, but how does this architecture actually perform when things go wrong in the real world? Let's throw some curveballs at this design, stress test it a bit, and see how it holds up.
So here's a classic situation. Your garbage collection is running behind, which, believe me, happens all the time in big systems. A request comes in for a paste. Its TTL is long past, but the actual data blob is still sitting there in your object storage. What's the system supposed to do? The system returns a 404 not found error. And here's the thing you have to burn into your brain. This is 100% correct behavior. It is not a bug. It's not a data leak. Why? Because correctness is enforced on the read path by that TTL check in the metadata. The physical state of the blob just doesn't matter to the logical state of the paste.
What's really cool is how gracefully this design handles other failures. If your metadata database goes down, no problem. We can probably still serve a bunch of popular pastes right from a cache. If the object storage goes down, okay, reads will fail, but they'll fail cleanly. And what if all your garbage collection workers just die? You know what happens? Nothing, except your storage bill goes up. The correctness of the system is perfectly fine.
So let's wrap this all up by really cementing the most important mental model here. And I want to talk about a very common and really dangerous mistake. I like to call it the principal engineer trap.
This is the trap. Some well-meaning, smart engineer looks at this and says, hey, to be more efficient, let's just trigger the deletion of the data blob from storage the instant its TTL expires. It sounds so logical. It sounds clean. And it is absolutely catastrophic. See, when you do that, you're tying correctness to cleanup. You're coupling them. And that means if 1,000 really popular pastes all happen to expire the same second, you suddenly trigger 1,000 delete operations. You create what's called a delete storm that just hammers your object store. This can cause your entire read path to stall out, creating huge latency spikes across the whole system, all because you violated that core principle of separation.
So look, if you take just one thing away from all this, let it be this. A service like Pastebin is at its heart a time-bounded object store. Time and only time defines whether an object is valid. Garbage collection, the cleanup, that only defines your operational cost. Keep those two worlds completely separate, and you'll build a system that's not just correct, but is also resilient and can truly scale.